Hello everyone! Today I will be showing you how to work a stoichiometry problem. The problem we will be solving today is modeled on the chemical equation pictured in the bottom left. The question is, how many moles of water are required to produce 2.15 moles of oxygen gas? The first step to solving the problem is figuring out what the question is really asking for. In this case, the question is asking for moles of water. So that is going to be written in the unknown section of this chart. Next, we shall find what the question has given us to help solve the problem. In this case, the question has given us 2.15 moles of oxygen gas as a starting point, and that should be written down in our given section. Now that we have our given, and we know what the question is asking, we can identify what the conversion factor will be. In this case, since we are going from 2.15 moles of O2 to moles of H2O, we can now know that the conversion factor is from moles to moles. Now it is time for the dimensional analysis. On our dimensional analysis chart, we will start by writing down what we know in the first top left-hand corner. And then below that, we are going to put the actual amount of oxygen that is found in our chemical equation, which in this case is 1 mole of oxygen in the gas form. Now here is where we're going to put the parts that we know. In this case we are going from the 2 moles of H2O to the 1 mole that was expressed at the beginning of the equation, which is the 1 mole of O2. Then we just multiply across and we get 4.3 over 1, which is not going to be expressed, so the final answer is 4.3 moles of water.
Rockets and the fuel that propels them to great heights are in some shape or form used daily.
The compounds that are found in rocket fuel are also the essential components of the fuel used in jets and helicopters.
Part of the science behind them heavily relies upon chemistry and stoichiometry. There are 2 types of rocket fuel, solid propellants and liquid propellants. Liquid propellants involve more chemicals and reactants than do solid propellants. In liquid propellants, there are 2 separate propellants, a fuel and an oxidizer. Standard fuels are kerosene, alcohol, hydrazine, and liquid hydrogen. Oxidizers include liquid oxygen and fluorine. The amount of chemicals must be balanced to perfection. Maximum results must be achieved as some propellants may ignite upon contact.